Okay, we are doing 16 through 20 now. Number 16 says you should be able to determine whether a bond formed between two covalently bonded atoms is polar covalent or non-polar covalent. Remember, the dividing line between polar covalent and non-polar covalent is 0.3. That's the electronegativity difference between those two. Remember also that the electronegativity difference of greater than 1.7 indicates an ionic bond. But we're going to focus on number 16 on non-polar versus polar covalent bonds. So if there are two atoms and they're both on the left side of the periodic, or excuse me, on the right side of the periodic table. So we're talking about two atoms on the right of the zigzag line, and they have electronegativities that do not exceed 0.3, or electronegativity difference that does not exceed 0.3. And it's pretty much going to have to be a diatomic molecule in order for that to happen. Then you're going to have a non-polar covalent compound. So non-polar covalent compounds mean that there's virtually no electronegativity difference between the two atoms. If you have atoms that have a greater electronegativity difference than the 0.3, then you're going to have a polar covalent bond. So polar covalent bonds happen when you have electronegativity difference of above 0.3 but below 1.7. So that should take care of number 16. Number 17 says, give examples of ionic compounds. What structures do ionic compounds form? So here's an example of an ionic compound. It is NaCl. And NaCl, as you can see, is composed of alternating units of sodium and chlorine ions. Sodium and chlorine ions alternating one after another after another. And so it is this electrostatic interaction, a positive and negative interaction, that's going to hold these atoms together fairly tightly, fairly securely. So, what structures do ionic compounds form? You should know that ionic compounds form a crystal lattice. They form a crystal lattice. Like you see, for example, in salt, the crystals, those are the direct results of this lattice work that you see in an ionic compound. So NaCl would be an example. Number 18. Number 18 says, give examples of covalent compounds. What is the basic unit of a covalently bonded compound? Do covalent bond compounds conduct electricity when dissolved in water? So let's take the first question first. Give examples of covalent compounds. Examples of covalent compounds, we talked about a number of those in class. For example, water is a covalent compound. The hydrogen and oxygen atoms are bound together via polar covalent bonds, but covalent bonds nonetheless. So anything where the electronegativity difference is sufficiently large for it to be, or sufficiently small for it to be covalent, are the types of bonds that we're talking about. The basic unit of a covalently bonded compound, of course, is a molecule. For example, water is a molecule that's covalently bonded. Do covalently bonded compounds conduct electricity when dissolved in water? No, they don't. Ionically bonded compounds will dissolve, when they dissolve, form or conduct electricity, but not covalently bonded compounds. That takes us to number 19 now. Give an example of a metallic compound. What are some of the most important structures of metals? The important thing to remember about metallic compounds is that they are very, we'll go all the way to metallic compounds. I'll take you to the two different slides later on. The important thing is the metallic compounds form bonds that are very, very strong. And those strong bonds require a lot of energy to overcome. So it is because of that that the melting points and boiling points of metals are very, very strong. The most important properties of metals are for example, their malleability. They can be hammered into various shapes. Their ductile ability. They can be pulled into wires. They conduct electricity very, very well because of the sea of electrons that exist over the metal ions. So that's number 19. And finally, number 20, be able to draw and evaluate Lewis structures. So I've drawn a few of them on the board, and let's go ahead and look at those. Let's talk a little bit about iodomethane. Iodomethane is this one right here. We have CH3I, and this is the way that we'll do Lewis structures. The first thing we want to do is we want to isolate what atoms are involved. So in this case, we have carbon. We have 1, 2, 3, 4 valence electrons. We only have one carbon. We have 3 hydrogen atoms. Each one of those has 1 valence electron. And we have 1 iodine atom. And the iodine atom has 1, 2, 3, 4, 5, 6, 7 valence electrons. We'll count up valence electrons now, and we'll make sure that we have the correct number of valence electrons for a structure. We have 1 times 4 valence electrons. We have 4 valence electrons being contributed by the carbon, we have 3 valence electrons being contributed by the 3 hydrogens. That's a total of 3 valence electrons. We have one iodine atom, and that one iodine atom has 7 valence electrons for a total of 7. That's a total of 14 valence electrons that have to be distributed over the structure. So let's put carbon in the middle. We always do when carbon is present. Carbon always goes in the center. We'll put hydrogen here. We'll put hydrogen here. We'll put hydrogen here, and we'll put iodine right there. We want to distribute these 14 electrons, so here's how we'll do it. We'll connect the basic skeleton, 1, 2, 3, 4, 5, 6, 7, 8. That allows us, that we have still an additional 6 more electrons to distribute. So we can't put them on the hydrogens because hydrogens only take 2 electrons each. We'll put them on the iodines. 1, 2, 3, 4, 5, 6. We'll ask 2 questions now. Do I have the right number of valence electrons? 2, 4, 6, 8, 10, 12, 14. I do. The second question is, does every element other than hydrogen have the requisite 8 electrons? 2, 4, 6, 8, yes. 2, 4, 6, 8, yes. So that's a viable structure for iodomethane. Let's look at ammonia now. Ammonia has a nitrogen atom, which has 1, 2, 3, 4, 5 valence electrons. Hydrogen has 1 valence electron, but there are 3 of them. So there's 1 nitrogen and 3 hydrogens. If I add those up, I have 1 times 5, that's 5 valence electrons, and I have 3 times 1, that's 3 valence electrons, for a total of 8 valence electrons to be distributed. So let's do that. So nitrogen in the center, we have hydrogen surrounding here, there, and there. Now what I'm going to do is I'm going to distribute as many of the 8 as I can. Just to connect the skeleton, I have 2 here, 2 there, 2 there, and an additional 2 that are non-shared right there. I have no choice but to put them there. I'll ask the question, do I have the correct number of valence electrons? I do. I have 2, 4, 6, 8 on the nitrogens. The nitrogen, again, has a non-bonded, non-shared pair. So that's that. I'm going to erase this now so I'll have a little bit more room for the next one. The next one is called ethylene. And ethylene has 2 carbons and 4 hydrogens. So here I go. So I have 2 carbons, and each carbon has a valence of 4 electrons, and each hydrogen has a valence of 1, but there are 4 of them. So I'll add up valence electrons. I have 2 times 4. That's a total of 8 valence electrons. 4 times 1, that's a total of 4 valence electrons. When I add those up, I have 12 valence electrons. So 12 valence electrons are distributed over this structure. I have carbons in the middle. I'll put a carbon right there and a carbon, I'll put a carbon there and a carbon there. I'll put a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen right there. And now I'm going to put enough of the 12 just to connect the structure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to have to put an additional 2 electrons somewhere. I'm going to put them between these 2 atoms of carbon to create a double bond. I'll ask the question, do I have the right number of electrons? I do. 2, 4, 6, 8, 10, 12. And the next question is, does every element other than hydrogen feel as though it has an octet? It does. Carbon 2, 4, 6, 8. Carbon 2, 4, 6, 8. I have the octet around both carbons. So I've got a structure. Notice the double bond in this molecule. And one final molecule is N2. Let's talk about how N2 could be drawn. So remember that nitrogen has a valence of 5. So I have 2 nitrogens. We have 1, 2, 3, 4, 5 valence electrons. So that's a total of 10 valence electrons that have to be distributed. The structure is going to be very simple because it's just 2 nitrogens. I'm going to connect the 2 nitrogens with a pair of electrons just like that. And that will take away 2 of the 10. I need to distribute 8. I'm going to distribute them this way. 1, 2, 3, 4, 5, 6, 7, 8. Will that work? Well, I have the right number of valence electrons, but not every nitrogen feels as though it has 8 electrons. So what I'll do now is I'll simply make a triple bond right here. I'll take these 2 electrons right here, and I'll put them right here. 1, 2, 3, 4, 5, 6, 7, 8, and I have a viable now structure for N2. That takes us to the end of there, and we are done.